started. Did you have any questions before I do get started? Okay.
No.
Well, we're well into chapter 19, so I'm going to try to knock out a good fraction of it. So I've got a series of examples. Again, not trying to do the derivations and stuff of that sort. I'm trying to just get through some problems to be solved so that you guys will better understand how to solve problems. So I've got them written up. I've left a blank page in case I need more than one page, and then I'll move to the next. So let's go ahead and get started. We are in the section on calorimetry now, so we're really solving calorimetry problems. So let me show you how to do this. Example one, I'm going to go ahead and share my screen because I forgot for a split second there. Sometimes you gotta narrate the situation or you're just not going to get stuff done properly. Hey Josh, how you doing?
Doing well. How are you?
Not too bad. I take it you're busy. I see you're not able to normally get here on time for work from work, I guess. So I figure
I
work's taking its
I'm
toll on you.
attending from work right now, so
Oh, gotcha. Yep, that's the nature of it. Well, I
yep.
have a problem here. I'm working now. Just this is very much like the examples in the book. I've tried to change them enough so that I wouldn't be violating any copyright issues. So hopefully that works. Uh, how much energy will your freezer remove from 1.35 kilograms of water at 22.5 degrees Celsius to make ice at negative 10 degrees Celsius? So, what we learned, especially from a very specific figure in your textbook, which let me look up that figure real quick. This is very important in the section on latent heat. It's figure 19-5. I highly recommend you start reading section 19.5, the latent heat, that whole paragraph before that figure, and then the paragraph after it so you can better understand what that's saying. But that really gives you a robust accounting of exactly what these heats of fusion and heat of vaporization is, or even heat of sublimation, so on and so forth. The main equations that we're using, of course, for this are the following. I'm going to write solution like I normally do. Oops. Actually, I wrote it just like I normally do. Crappy. So solution like this. Now the equations we'll be using are Q is equal to mc delta T. That's the equation that tells you how much heat Q must be added to a mass M of a substance that has a specific heat C to change its temperature by an amount delta T, which is supposed to be T final minus T initial. Again, I'll remind you that that delta, that capital delta, which is the triangle that you see there, unless they explicitly tell you otherwise, in the engineering, physics, and chemistry world, delta always means final minus initial. And in this calorimetry section, I often have to violate that because the way I like to solve my calorimetry problems is I say all the stuff that's hotter than everything else, i.e., it's giving away heat, is on one side, and then all the thing that's colder than everything else, i.e., it's absorbing heat, I put it on the other side of the equation. And that way I have nothing but positive signs on everything. I don't have to think about whether the heat of fusion is a positive or negative, if I'm going from liquid to solid or from solid to liquid, all that good stuff. So just remember that. The other equation I'm using is Q is equal to M times L, where L is the heat of vaporization, or heat of fusion, or more specifically and generically, latent heat. So there's an additional amount of energy that's required, for instance, if you're going from solid to liquid, to breaking up the molecular slash atomic bonds between adjacent atoms slash molecules in the lattice in transitioning from solid to liquid. And then there's another one. That one, by the way, is heat of fusion, technically going the other way. And then there's another one in going from a liquid to a gas, and that one's called the latent heat of vaporization. And that's the amount of heat that you have to add to break up the molecular slash atomic bonds that are holding atoms and molecules, atoms slash molecules, close to each other while they're in the liquid state. Remember, they're not quite as far apart as they are in the gaseous state, and they're a little further apart than they are in the solid state in most cases. In this case, they're sort of somewhere between. So when I figure out how much energy my freezer has to remove, I've got to think about the water, which has initial temperature of 22.5 degrees Celsius. I've got to think about it and its specific heat in the liquid state to bring the temperature from 22.5 to zero. Then I got to think about the heat of fusion, or depending on which way you're going, obviously, required so that I could actually make it freeze. And then I've got to figure out how much heat I'm going to have to take away to bring the now ice, i.e., solid water, to negative 10.0 degrees Celsius. Okay, because there's no guarantee that the specific heat does not change from one state to another. In fact, your book has listed the specific heat of water in calories, anyways, in calories per gram Celsius degree, is 1.00 calories per gram Celsius degree. We know that's from 14.5 to 15.5 degrees Celsius. But if you consider again water, but this time as a solid, it turns out that that specific heat is 0.50 calories per gram per Celsius degree. And as steam now, it's even weirder, which it's not very necessarily very good to talk about specific heats of gases. As you'll see later, there's a very specific way we can talk about them so that they'll be helpful. But in this case, for water, it would be 0.48 calories per gram Celsius degree, or excuse me, I'm sorry, I put Celsius degree in the bottom of all those denominators. No, that's right. I was talking about specific heat. Sorry, I thought I had switched to heat of fusion already, or latent heat. So yeah, it is 1.00 calories per gram Celsius degree for liquid water, 0.50 calories per gram per Celsius degree for solid water, and 0.48 calories per gram per Celsius degree for steam. So now that we have that, I've got to use the plan that I just laid out. And the plan that I laid out, of course, was that we've got to figure out how much heat it takes to bring the 22.5 degrees Celsius water down to 0 degrees Celsius. Then we got to figure out how much heat has to be removed to force that to go ahead and go from that liquid state at 0 degrees Celsius to the solid state at 0 degrees Celsius. And then I've got to figure out how much heat it's going to take to be removed to take that 0 degrees Celsius ice and turn it to negative 10 degrees Celsius ice. So the total equation is going to be Q is equal to M water, C water. Now notice I'm doing water and I'm going to put an L on it. That's because it's in the liquid state. And in this case, I'm actually going from a high temperature to a low temperature. So the delta T would actually be negative. I don't want that. I just want to figure out how much energy total. So I'm going to do big number minus small number. That's going to be T initial minus T. Well, I'll actually, since I'm going to 0 degrees Celsius, I'll just put that number in because it's easier to do that. And now you can tell that no matter what I put there, unless it's a negative number, the Ti is definitely going to give me minus 0 is definitely going to give me a positive quantity. So that should bring it down to 0 degrees Celsius. Plus, I'm going to have the mass of the water times the latent heat of fusion of in positive terms, but the heat of fusion for water. And that is basically once I've got the water down to 0 degrees Celsius, I then have to remove even more energy to allow it to become a solid as opposed to a liquid. So that'll account for that part. And then I've got to use the mass of the water times the specific heat of water, but this time not in the liquid state, but in the solid state. So I'll put a S there. And this one's going to be from 0 to negative 10. So if I actually do 0 minus negative 10, that'll be positive. So 0.00 degrees Celsius minus 10.0 degrees Celsius. And that should be the whole equation. Now all I got to do is enter the data. Does anybody have any questions on this? Okay. One thing you can see is I'll have the same mass for water in all cases, so that'll save me a little room, and I'll just factor that out in front. I'm going to say 1.35 kilograms. Now, the C for the water, uh, I've actually got the latent heat. I actually looked that up in terms of, oh yeah, I did it in joules. So I'm going to do this in joules as well. So instead of using 1.00 calories per gram Celsius degree, I'm going to use 4,186 joules per kilogram Celsius degree. So that's the specific heat of water. In this case, I'm going to put a square bracket around there so that we remember that mass is going to be multiplied by each of these terms. So I've got 4,186 for the C of water. Now I've also got this factor of 22.5 degrees Celsius minus zero point 0.0 degrees Celsius, like that. That's the first term. Now all I have on the second term, since I've already factored out the mass of the water, is just the latent heat of fusion, which is 3 point, or let's do it 3.33 times 10 to the fifth, and that is joules per kilogram. Notice that one just has those units, no Celsius in the bottom, which is why I tried to correct myself a little bit earlier. And then finally, I've got the mass of the water, which I've already factored out in front, times the specific heat of solid water, which I told you was about 50 or 0.50 in calories, but we're using it in joules. So that's going to make, it turns out, about 2,100. It's really only to 2 sig figs, I think. But anyways, that's joules per kilogram Celsius degree times, now in this case, 0.00 degrees Celsius minus 10 point minus negative 10.0 degrees Celsius is 10.0 Celsius degrees, like so. And now I can box off everything. It looks like I'm not going to have a problem with fitting it all in one page, so I'll erase the extra pages before I post these to my Google Docs. But let's start off with the 1.35 out in front. I'm not doing anything with that yet till I uh, finish up the stuff inside the square bracket. So I'm taking 4186 times 22.5, and that gives me 94,185. And that, of course, turns out to be just joules per kilogram because we're going to multiply by kilograms a little later. The next one is, we can call that 300 or 33. Yeah, this is 333,000. So I'm going to write 333,000, and that would be joules per kilogram. Again, and that's for the middle term. Remember, it was 3.33 times 10 to the fifth. That would make it 333 times 10 to the third. And 10 to the third is the same thing as kilo, so that's how I work that out. And now finally, I've got 2,100 times 10. That's obviously going to be 21,000, so I'll say plus 21,000. Again, joules per kilogram. Now, the big thing to realize here is I had 3 sig figs in this first thing, so this 8 and this 5 are not sig figs. In this second term, I had 3 sig figs, so basically the ones, the tens, and the uh, hundreds are not significant in this middle term. And the last term, I'm pretty confident that's only 2 sig figs. So I'm going to say that the hundreds, the tens, and the ones are also not significant in that third term. That means that it's not significant in any of them because these are all being added. So I'm going to take 94,185 and I'm going to add to that 333,000, and I'm going to add to that 21,000. And just remember that the hundreds place is not a significant figure. So I've got 1.35 kilograms times, in this case, it turns out to be 448,185 joules per kilogram. Of course, as I said, the hundreds place, the tens place, and the ones place are not significant, so I can't do more than that. But now I can go ahead and multiply this number by 1.35, and that will get rid of the kilograms and give me the total number of joules. And that total number of joules looks like about 605,000. So I'm going to see, and it's basically comma 049.8, and that's just plain joules. Actually, I should probably write that joule uppercase. But none of these digits are significant. So the final answer I should really write as probably 605 kilojoules, and that should be basically how much heat can be removed or will need to be removed by your freezer. Any questions on that one? Okay. And you'll notice this looks a lot like the problem 19.6. Uh, and in the problem 19.6, we had different numbers, and they got around 660 kilojoules. So that does seem consistent with this one. Now, I was afraid that my work, because the width of this isn't that good, I was afraid that my work might actually take more than one page, so I had this blank here. I'm going to remove that after the fact. But we're going to go on to example 2 now, which is this one. Again, this is not unlike an example in your book, but I'm trying to not get in trouble with the publisher. So let's see what happens. You are trying to make iced tea. I don't know if you know that, but that phrase iced tea, at least down here in the South, strictly speaking, normally means super, super sweet, but not always. But it definitely means cold. So the ideal scenario is you've got so much ice in it that all the liquid is 0 degrees Celsius.
well, wouldn't that change our chemical makeup?
When you put all that sugar, yes, absolutely.
Yes,
I didn't,
exactly.
I didn't necessarily know that, but I had a guy in the Navy a couple semesters ago. For some reason, even though his expertise was in science, he ended up being a cook in the Navy, and he happened to one time, I guess, do something to figure out the density of his tea that he was making, and sure enough, it was significantly different. And he did some other experiments on specific heat and found that it was significantly different. So yeah, at least with sweet tea, I know it can change a bit, but still going to pretend it's water.
All right.
All right, so it says you are trying to make iced tea, so you take 3.00 kilograms of tea at 22.5 degrees Celsius. You know, you normally have to boil bags, and then you pour that into like a gallon or something of water, and that makes it, of course, no longer boiling, but still pretty warm. But I left it closer to room temperature here. Well, at least make a fat man scream temperature. That's a horrible temperature for me. Uh, but anyways, 22.5 degrees Celsius, and you put in two 0.782 kilogram blocks of ice at negative 11.5 degrees Celsius. So basically, blocks of ice usually don't come much bigger than a kilogram. And if you could even get them at a kilogram anyways. So I tried to imagine different numbers, but again, I wanted it to be significant on the order of 1.5 kilograms or higher, and therefore I went with these numbers. So it'll be two of them. We got to keep track of that. So what I would recommend doing when you have something like that is make sure you underline that. Okay, so you can remember that. With that in mind, it says, at what temperature will the new, somewhat watered down tea end up? And will it all be liquid? Okay, so that's a big consideration here because you actually have a bunch of different things that could happen, and you got to figure out which one's going to happen to make the calculation right. So what I'm going to do is see exactly how much heat it would require to bring this 3 kilograms of tea down to 0 degrees Celsius. And then I'm also going to see exactly how much heat you would have to extract from these two ice cubes to get it to 0 degrees Celsius. And then looking at those two, I can tell whether or not I have enough ice in there to really bring the liquid down to zero and not completely melt the ice. So that's what we're going to go with. Uh, Let's start with solution so we'll know exactly what equations we're going to be using again. In this case, we do have a changing of temperature, so we got to use our MC delta T. We also have a changing of state. We're going to melt some fraction of the ice. So not only are we going to take this ice that's negative 11.5 degrees Celsius and bring it up to zero, we're then going to go a little further and try to melt it. And then what happens is once that ice becomes water, it's free to change temperature like the rest of the water. So we got to make sure that we take into account that. The other one is, of course, changing state requires Q equals M times L, where L is the latent heat. I will go ahead and write down the key values we need. So, for instance, I'm going to say again, we're pretending like the tea is essentially water. So I'm going to say the specific heat of tea is supposed to be, it looks like we got a lot of kilograms here too, so joules would probably be better. So I'm going to say the specific heat of the tea is going to be 4,186 joules per kilogram Celsius degree. I see you, buddy. It's not helpful, though. Thank you. My dog over there all of a sudden decided he needed some attention. My other one's down under my feet. But anyways, so that's the specific heat of the liquid version of water, of course. The specific heat of the ice version, however, which I'll write as Ci, like that for ice. Oh my God, that's going to definitely cause confusion with a T. So let's go ahead and write it as ice. So the ice is going to be 2100 joules per kilogram Celsius degree. We also know that the heat of fusion of water, which actually I'll just write a W because it turns out that H and 2 and O is a lot more writing than just a W. So, so with this one, we know that the latent heat of fusion is 333 kilojoules per kilogram. Okay. I think that's just about it. We do have, of course, the mass of the tea. So the mass of the tea is equal to 3.00 kilograms. And since we have two ice cubes, we can go ahead and fix that right now by saying the mass of the ice is, and I'm just going to take my calculator and take this 0.782 and not trust myself one bit to do the multiplication in my head. I'm going to say 0.782 kilograms times 2. And it looks like I hit the multiplication symbol, which is a good sign. So that's 1.564 kilograms of ice. So now we don't have to worry too much about that 2 anymore. But let's go ahead and see. So first off, I'm going to answer the question, how much heat must be removed from 3.00 kilograms of water. I put that in quotation marks, just reminding us that we're treating it like water, but it's not water. So to remove from 3.00 kilograms of water at 22.5 degrees Celsius to bring it to 0.0 degrees Celsius. So that's the first question we're going to try to answer. So right now I'm going to say Q for the water, or specifically for the tea. So QT is going to be 3.00 kilograms times the specific heat of water, which is 4,186. Uh, Now this time it's joules per kilogram Celsius degree. And then I'm just trying to figure out the magnitude of this quantity. I don't want any negatives or anything like that. So I'm just going to take the big temperature minus the small temperature, which would be 22.5 degrees Celsius minus zero point 0.0 degrees Celsius. Notice that when we subtract Celsius temperatures from one another, we call that Celsius degree, but I want to point out that there's really no physical difference between Celsius degree and degree Celsius. So we do use them, sort of run roughshod over what you might think are different units, but that's just because experience shows us that we can pull it off with no problems. All right, so let's go ahead and do this. I'm going to say 3 times 4186 times 22.5, and that should all be to 3 sig figs. And this gives me, in fact, 282,555 joules. And I want to remind everybody that these last three fives are not significant figures. So we now have that. Now what we want to do is see really how much heat can we put into the ice to allow it to come all the way up to 0 degrees Celsius and then melt. So now we're going to do that. How much heat added to the ice will cause it all to reach 0 point 0 degrees Celsius and all of it. How much heat added to the ice will cause it all to reach 0 degrees Celsius and all of it to melt. Okay, so that's the question we're trying to answer here. So this time I'm going to call this Q ice, and we decided to write the whole word because I'm clearly not that good of a thinker sometimes. So in this case, I'm going to take the new mass of ice that we got because now we know that we're using both ice cubes, 1.564 kilograms, which the sum of the two, three subject or significant figure numbers made us result in a 4 sig fig number, so that was kind of helpful. We are working with ice though, so we know the specific heat is not the 1 calorie or the 4,186 joules. It's actually, in this case, the 2,100. Oh, man, I hate it when that happens. All right. It's the 2,100, and this case is joules per kilogram Celsius degree, like that. And then, of course, we're trying to bring this from negative 11.5 degrees Celsius to 10, and I don't want any negative numbers, so I'm just going to say 11, or excuse me, I said to 10. Why did I say to 10? I mean to 0. So I'm going to take 0 minus the negative 11, just so I get a positive number. So I'm going to say 0 0.0 degrees Celsius minus negative 11.5 degrees Celsius. Now, it probably just been smarter for me just to write 11.5, but I thought this might be a little bit more faithful to the original formula and cause less confusion in looking in your notes later. All right, so remember, I am reversing the deltas all over the place here, and this is a calorimetry. That's pretty much the only place I ever do it, but keep it in mind, that's the way I do it, not necessarily the only way to do it. All right, so that gets our ice cubes from negative 11.5 up to 0, but now I've got to add enough heat to overcome the what we call the latent heat. So I've got to add as well to that 333 kilojoules per kilogram. So I'm now going to say plus 1.564 kilograms times 333,000 joules per kilogram. And when we compare our number that we get here to the number we got above, that can tell us what's likely to happen. So this time I'm going to take 1.564 times 2100 times 11.5, and that gives me 36,853. And that, of course, is just plain joules. And with this, it turns out that we had three sig figs. Yeah, I'm still pretty sure we only had two sig figs in that 2100, so I'm going to say the 8, the 5, and the 3 are not sig figs. Again, most instructors, me included, don't really worry about such things as sig figs in the lecture portion, but I'm trying to be pedantic so we all are on the same page and can do it right. 1.564 times 33 or 333,000 gives me 520,812 joules. Okay. Again, we had three sig figs. Well, actually, this time we have three sig figs. So again, the hundreds place, the tens place, and the ones place are not significant, exactly as we said before. So now I'm going to take this 520,000 and I'm going to add it to the 36,853, and that's going to give me 557,000, comma 665 joules. Again, these last three, the ones, the tens, and the hundreds places, are not significant. So it really seems reasonable to call this 558. In this case, it's 558 kilojoules. So, in order to melt all of the ice, I'm going to have to put in 558 kilojoules. But in order to bring the warmer tea down to 0 degrees Celsius, that's only going to cause us to extract 283,000. So clearly, the 283,000 is not enough to bring all the ice down. So what's obviously going to happen is uh, we're going to basically bring it down so that the tea will reach 0 degrees Celsius. Yes. So the tea will reach 0 degrees Celsius, and it'll be in or within the tea will be a block of ice. So now we can give that a try. Any questions on this one so far?
All
Great.
good.
You good? Okay, that's cool. No problem. So with this in mind, I want to make sure I didn't make any mistakes on the numbers. I thought I got entirely different numbers when I worked this earlier. Anybody find any arithmetic mistakes? 1.526. Where did I get 1.526? Yep, that's part of the problem. Somehow I typed in 1.526 times 2100 instead of 1.564. Let's check those numbers again. Everybody, what I'm talking about right here is this. I may not have put the right number in there, so I'm going to check that again. 1.564 times 2100 times 11.5. Yep, that's a different number. Okay. So
Well, is that 11, negative 11.5?
it is supposed to be negative of negative
Oh, negative.
11.5.
Okay, so it's gonna be a positive. Yeah, yeah.
Yeah.
Okay.
And I was actually trying to actively make all that positive anyways, so hopefully that works out. So this gives me 37,770. So I'm going to say 37,770 joules in this case. And again, probably only two sig figs, so those are not significant. Okay. And then the other one, 1.564 times 333,000. That gives me 520,812. That looks fine. Plus 37,770. Oops. Yep.
So I got 558, 582.
Yep. 558,582. Thank you, sir. Appreciate that. So not too far off, but definitely a little bit, and that's turned out not to be enough to really matter. But still, I'd much rather have it right. 583 roughly is 2.6. But again, the tens, I mean the hundreds place here, the tens place here, and the ones place here are not significant. So in this case, I'm going to call it 559 kilojoules. But again, the same result. It turns out that it takes way more heat to melt these two blocks of ice than it extracts from the hot tea to bring it down to 0 degrees Celsius. So the hot tea is going to come down to 0 degrees Celsius, and then basically some fraction of the ice will at least be brought up to 0 degrees Celsius, and then some fraction will start being melted. So what we're going to do is take and figure out exactly what that is. So what we're asked here is to say what the final temperature will be, and will it all be liquid? We've now answered the question to see that it will not all be liquid. Some actual there'll actually be some ice floating around in it. So let's do a equilibrium situation. So I'm using calorimetry here, and what I'm going to do is I'm going to say Q hot, meaning the hot thing, is equal to Q cold, meaning the cold thing. So what I mean by that is the hot thing is going to release heat. This is specifically the T. And the cold thing, which is specifically the ice, is going to absorb heat. So I can just set those two equal to each other and I don't have to worry about signs, but I do have to make sure all the terms that I use are positive. So, and that's both a problem and an advantage. In fact, it was specifically because the advantage of only having positive terms that I choose to do it this way. So we're going to take the hot thing, which is the T. So that's going to be the mass of the T. Is that what we used for it? Yeah, we did use T times the specific heat of the T times, in this case, we want it to be positive. We know the T is going to go from 22.5 to 0. So we're going to do instead 22.5 degrees Celsius minus 0.0 degrees Celsius, like that. Uh, that is that is basically this T giving up its heat to actually try to melt the ice cube, or the ice cubes plural. Now, at that point, that's pretty much the only thing we have to deal with. But on the other side, we have to deal with what the ice is doing. Now, the way ice will behave, or the way matter behaves, is all of it will be brought down to 0 degrees Celsius, or up to, I should say, 0 degrees Celsius, and then it'll start to be chipping away at the melting process, and only a small fraction of it will melt. But in some sense, we're going to assume that that small fraction is going to stay the same temperature, so I don't have to keep adding it to it. And let's see what happens with that. So in this case, I'm going to get the mass of the ice times the specific heat of the ice times, in this case, I need a positive, and I know I'm going from negative 11.5 to 0, so I'm going to do 0.0 degrees Celsius minus negative 11.5 degrees Celsius, like that. Notice it's a minus a negative. Actually, that's really horrible. Let me write that a little better. I try to fit that C in after the fact. Minus negative 11.5 degrees Celsius. And then I also have the mass of the ice. In this case, it's not necessarily going to be all melted. So the mass of the ice melted would just be this little quantity. And then the latent heat for the ice will be there. So what I'm going to do is I'm going to set all this equal to each other and use that to actually solve for the mass of the ice that's been melted. Because it's basically all it can do is melt some fraction of the ice. Uh, and then it can't even start bringing that water that was formerly ice. It can't start bringing that necessarily up in temperature, or at least we're going to go like that, act like that's a small amount. So I'm going to lasso using my iPad. I'm going to lasso this last equation, and now I'm going to copy it, and I'm going to put it on the next page, and I'm going to paste it. Okay. So now we've got this equation up here. I can start putting the numbers in. Crap, I don't remember the numbers. No, 1.564 is the mass of the, no, the mass of the T is 3 kilograms. So that's going to be 3, whoa, Nelly, writing with the wrong thing. That's going to be 3.00 kilograms times 4,186 joules per kilogram Celsius degree. Now, this time I'm just going to write it as 22.5 Celsius degrees, and that's all the math for that part. On this side, now we have the mass of the ice, which is 1.564. I don't even know where that other number came from that I used before. Kind of weird, but anyways, now the specific heat of ice is 2100, and this is joules per kilograms Celsius degree. And now in that case, 0 minus negative is a positive 11.5. So I'm going to say 11.5 degree or Celsius degrees, say. And then I'm going to say plus M, I'm just going to call that IM for ice melted, times L, which is 33 or 333,000 joules per kilogram. And I'm just going to solve for what that MIM is. Okay, so let's go ahead and work out the numbers that we do have. So I have 3 times 4186 times 22.5. That's clearly a 3 sig fig answer. So that's 282,555 joules. Again, those last 3 digits are not significant. That's going to be equal to 1.564 times 2100 times 11.5. And this gives me 37,770.6, which is a number that should look familiar to us. And we got that. And of course, that is joules, by the way. And then we just have equals 300. Oh, it's not equals, that's plus. Sorry about that. I'll just make it a plus from there. Plus, in this case, it's going to be M times 333,000 joules per kilogram, like that. So what I'm going to do is subtract 37,770 from both sides. So 282,555 minus the answer I just had, which was 37,770.6. This gives me 244,780. I'm going to call that 5. It actually was another decimal point, but I didn't really see much use in doing that. That's from taking the 37,770.6 from both sides. And now that's equal to M times 333,000 joules per kilogram. So if I divide both sides by 333,000 joules per kilogram, I'll get just kilograms for the units on the left. And I'll just get just M on the right. So I'm going to take this 244,785 and I'm going to divide it by, I'm actually dividing the 784.4. I'm going to divide that by 333,000. And that gives me 0.73508. Obviously, two extra sig figs there. Actually, that should be 0.9 to be honest with you. I hate being such a pedant, but here I am. And that's kilograms is equal to M. Notice that's almost the size of one of the ice cubes. So basically, one ice cube will be completely uh, almost complete. Let's see, what was that? 782. Yeah, so this is both of them have some melt on it, obviously. Me breaking it up into two separate ice cubes might have made a little philosophical problem that we'd have to work out a little bit more because now I would be inclined to work it out as if I know for a fact that 1.564 minus 0.735, I know for a fact that that's going to melt. So then I could go back and just put that in with the mass of the water uh, once we get to zero, and we get another calculation. But I'm going to go ahead and say that this is good enough. Okay, I would probably choose the quantities a little wiser if I was doing this for a test, so there wouldn't be something ambiguous pop up like this, like the one in your book. What they ended up doing was, oh, they had that the water, the tea basically took 250,000 joules to bring it down to zero, but the change in temperature of the ice and the change of state of the ice gave 177. So it was way, way more. That's actually pretty much what I had too. I had 559. They had 160 or 177. And then they had 250 for the top one. I had 280. So yeah, it's sort of the same scenario. But like I said, I might have introduced a little bit of a problem by suggesting two separate ice cubes. That's one of those bummers where if you've ever happened to be fortunate enough to know a little bit of information, it might actually get you in trouble. And that's what I did because I happen to have carried ice in solid states before. Have you ever bought, either of y'all ever bought an actual ice block as opposed to a bag? You don't see them too often, but some places have them.
No, but I remember the old ice box freezers with the place for it.
Yep, yep.
I mean, we had, I mean, I know this is different properties, but I had to deal a lot with dry ice.
Oh yeah,
We had to
yeah.
buy it in large quantities and
Oh,
yeah,
that's kind of
ship.
interesting.
Well, it
Is
was
it for
for
shipping stuff?
yeah, well, it was for we were doing fish sampling and we had
Oh,
to
okay.
send in tissue samples and also water quality samples to
Oh,
a
cool.
lab to get it analyzed, and we had to carry well, we were in the middle of nowhere, so we had to ship these in coolers and send them to like FedEx. And yeah,
Make
we
sure to
had to
stick don't
carry
rub away.
like 70 pounds of dry ice on us at all times. Finding it was a pain in the butt,
Yeah,
but
Yeah.
yeah. You have to find a scientific supplier or a medical supplier and
yeah,
buy it in bulk, I reckon.
yep.
Yeah, I've had some engineering, quote unquote, engineering jobs like that before. I think I might have told you guys about me having to sit there for, I swear it was a couple of months counting friggin' dump trucks, which I was low man on the totem pole. I was paid the least and billed at the most compared to my pay. So they sat me in a car for 8 hours a day counting dump trucks and noticing whether they're 6 cubic yards, 4 cubic yards, 10 cubic yards, 12 cubic yards. And I kept all these cards on it, and I just listened to Rush Limbaugh all day. But we were literally moving what had blown off of Jockey's Ridge to the south. We were moving it all to the north side of Jockey's Ridge so it could start it over again. That's our that's our tax dollars. So,
Is that
anyways,
under a contract?
Yeah, yeah. They do it about, last I heard it was like every 5 to 8 years or something like that. They have a bunch of bidders come in. They've already bought the property on the north side, yeah, the north side of the street just south of Jockey's Ridge. So there's houses that were really quite nice, but they're covered in sand. And we basically just move all of them from there with a front with an excavator. He loads up the dump truck, and we get like 18 trucks in a line, and they just all drive continuously until we moved. I think I moved 100, no, 216,000 cubic yards of sand. We did a aerial view and did a topo of it, and then I had to calculate roughly how many cubic yards that was from the topo, and then followed out the project. And they let me sit there. I say let me. It actually wasn't too bad. Probably horrible for my health. All right, let's go ahead and get started
I
on the
just
next one. Go ahead.
I did a site plan not too far away, or a concept plan, I should say, for a developer not too far away from there,
Hmm. Oh
just a
yeah.
couple weeks ago.
Oh, that's
Yeah.
cool.
Yeah.
So yeah, working out on the Outer Banks. Rock on.
I
All
mean,
right.
it's few and far between. We never really get these jobs, but
Your place is out of Virginia Beach or Norfolk?
we're in Portsmouth, but I mean, we serve developers all over
Yeah.
the place, pretty much all up and down the East Coast.
Cool. Don't say more about your company unless you know that you can, because
Yeah, that's
sometimes
fine.
people don't
I'll leave
want
it
to do
there.
that. Okay,
They can
that's
take a
cool.
wild stab at it. Good luck.
Okay. Yeah, exactly. There's no engineering firms in the Tidewater area. Okay, how about this? Example three. It says a 1.34 kilogram uh, 1.34 kilograms of solid mercury at its melting point, negative 39.0 degrees Celsius, is placed in a 0.523 kilogram aluminum calorimeter filled with 1.35 kilograms of water. Whoa. I did not mean to make them that close, but I did. 1.35 kilograms of water at 22.5 degrees Celsius. If all the mercury is melted and reaches 17.3 degrees Celsius, what is the heat of fusion of mercury in joules per kilogram? So this is one where we could try to experimentally determine the heat of fusion in this case. So again, I'm going to set it up such that one thing is the hotter object and therefore is giving off heat or losing heat, and then the other thing is the colder object and it's gaining heat. So you could also call it Q loss and Q gain. Let's go ahead and start with my solution. As always, put my equations. Obviously, we're going to have Q equals MC delta T. We're going to have Q equals ML. We're also going to have Q lost equals Q gained. Some more wording that I occasionally use, mainly because I can't remember from one week to the next what words I used last time. So they tend to meander a bit and figure out what what words I'm using. So in this notation, what I'm meaning is the hotter object is losing heat, and in a calorimeter, we expect a good fraction, hopefully very close to 99.9999%, actually very close to 100%. We hope all of that is being gained by the other thing. So that's the major equation we're using. Uh, so the thing losing the heat obviously is the water and the aluminum cup. So I'm going to start off with, ooh, did I give myself the did I give myself the mass of the aluminum? Yes, I did. Okay, phew, scared me. All right, so the water and the aluminum cup are the heat lost. I'm going to need some data about those. The data I have, for instance, is the specific heat of liquid water, which I'm just going to call CW, is obviously 4,186 joules per kilogram Celsius degree. We're also going to need it for aluminum. The specific heat of aluminum is 900 joules per kilogram Celsius degree. We'll also need we're actually trying to solve for the latent heat of the mercury, heat of fusion in this case, and that's LFHG is equal to question mark. So that's what we're looking for there. We do know the mass of the mercury. and that is the mass of the mercury is 1.34 kilograms, and we know the mass of the aluminum is 0.523. Oops, I just left out a 2. 0.523 kilograms of aluminum, and we know the mass of the water is, there I go again. Let's not do that H2O stuff. Just be more efficient. Oh, there it goes. I want to make that into a W. Look how efficiently I did that. The mass, the mass of the water is 1.35 kilograms. Like that. And what we have is that the aluminum and the water should have the same temperatures. So T final for the aluminum, actually T final is the same for everything. So I'm just going to put T final and just call it that. And we know that's going to be 17.3 degrees Celsius. We also know that the T initial for the aluminum and the water is going to be 22.5. And we know that the initial temperature for the mercury, T initial Hg, is negative 39.0 degrees Celsius. Okay. So now I can write Q lost equals Q gained. As I said, the water and the aluminum will be the warmer things and they're losing the heat. So I'll put those on the left-hand side. The mass of the aluminum times specific heat of the aluminum, uh, and then times the change in temperature, which I'm going to go ahead and put that in now, just to help us remember that we got to keep it in a positive order because again, I'm not using the formal definition of the capital delta. I'm making all the terms positive. So in this case, the aluminum is actually going from 22.5 to 17.3. So I'm going to do 22.5 minus 17.3. And then because I forgot to put the units on there, I'm going to put, actually, I'll put it this way. I'll put Celsius degrees. Okay. So 22.5 minus 17.3, that gives us the positive value, and that is the actual range that we're supposed to go through. So I haven't made any mistakes there, but that's just the aluminum who's really only going to change temperature. It doesn't change any states or anything like that. Now we also have the water doing the same thing. So the mass of the water times the specific heat of water, and this time the water, of course, is also going from 22.5 to 17.3. So again, I had to put it in that opposite order. And again, I clearly forgot to uh, put the units. So Celsius degree it is, and I'm going to make that into a square bracket. So at least I'm consistent on my mistakes. And Jen had to leave us, I know that. All right, so we got the water changing state, and that's really all that has to happen on this side. The other side, however, we have to have the mercury brought down from negative 39 degrees Celsius up to and that might have been something I needed, specific heat of mercury. Yeah, I didn't look that up, but I will get it. It's not a big deal. So now I have to take the mass of the mercury times specific heat of the mercury. And this time I've got to bring it from negative 39 up to zero doesn't matter here because it's not water. Its critical temperature is negative 39. So what I'm going to do is 17.3 minus negative 39. So this one's 17.3 degrees Celsius minus negative 39.0 degrees Celsius. That time I did remember the units, so that's good. But I also have a term for the mass of the mercury times the latent heat of fusion for mercury, and that's the variable that we're trying to solve for. So now I can go ahead and put some of these numbers in hopes of making it a little more clear. So what I'm going to do is the 22.5 minus 17.3. I'm going to work that out so that I can put that number by itself, and then just fill in the numbers so it won't take up quite as much room. So 22.5 minus 17.3 gives me 5.2. So this is the mass of the aluminum, which is 0.523 kilograms times 900 joules per kilogram. I'm going to assume that's 3 sig figs. That's not a very smart thing to do, but I'm going to do it anyways. And that's Celsius degrees as well. And then times 5.2. Let's make that degrees, Celsius degrees, just to be a little pedantic, which I finished just telling you that there's really no difference in them. Oh boy, I did not leave myself much room. Let me fix this real quick. Let's do cut. Let's do paste. So I'll put it down this low. That should be fine. All right, so I've got that figure. Now I've got the mass of the water, which I need to write with the writing utensil. So the mass of the water we said was 1.35. The specific heat of the water in the liquid state is 4,186 joules per kilogram Celsius degree. And the change in temperature is also 5.2 Celsius degrees. And this is all equal to, I didn't really move it as low as I should have. Let's move it one more time. Cut, paste. That was pretty good there. So I've got that. Now I've got the mass of the mercury, which is common to both terms, so I can put that out in front, and that is 34. So I'm going to say 1.34 kilograms. That's going to be out in front. And then I'm going to take the specific heat of mercury, and the specific heat of mercury is 140 joules per kilogram Celsius. So 140 joules per kilogram Celsius degree times, in this case, it's 17.3 minus negative 9.0, and that gives 56.3 Celsius degrees. And then I've got this other term, which is 1.34 kilograms times the L that we're looking for. So what I'm going to do is add the two terms on the right after multiplying them. So 0.523 times 900 times 5.2 gives me 2,448. So 2448 joules. And there's really only 3 sig figs at best, so I'm doing that. The other one, 1.35 times 4186 times 5.2. That is 29,385. Let's call it 386. Again, carrying the 3 extra sig figs. Not a problem there. And then that's equal to the 1.34 kilograms times 140 joules per kilogram Celsius times 56.3. And that gives me 10,562 joules plus 1.34 kilograms times the latent heat of fusion of mercury. So all I have to do is add that 2448 and 29,386 and subtract from it the 10, 562, and then divide by 1.34. That should give it. So 244 247.64. I am actually using the original number since I'm looking right at it. So I did the 2447.64 plus the 29,385.72. And then I'm going to subtract from the last answer I got, which is a 10,561.88. And that gives me 21,271.48. Again, really, there's no way I can get that 48 with the numbers that are shown up here. In fact, it'd probably be best for me to just show this as 1 and get rid of that decimal jump. Okay. So that's darn it. So that's it in joules. And of course, that's equal to 1.34 kilograms times the latent heat of fusion of mercury. That means the latent heat of fusion of mercury should be equal to 0.1271 divided by 1.34 gives me, whoa, that's a big figure. That gives me 15,874 joules per kilogram. Now I had 2 sig figs divided by 3 sig figs, so that only gives me 2 sig figs. So I'm going to have to call this approximately 16 kilojoules per kilogram, roughly. So anybody have any questions on that one? Well, anyway. Hey, Josh, got a
Yeah.
question?
No.
All right, that's cool. So I've got that done. That's a pretty decent example of calorimetry in sort of the hardest state. I'm also willing, if you want to think more about that example that I just did with the ice, if you want to try to come up with a way you think would work out, and in other words, in terms of knowing how much ice actually melts with the 2 cubes, you can turn that in as an extra credit if you'd like. But if you're too busy, don't worry about it. It's just an extra little bit of fun. I'd like to see what another student might think of it.
Yeah,
Now, go
I
ahead.
got a question too. Well, I got to split here in the next couple minutes. I got to go to lab. Um, did you announce the test yet?
Yes, it's. I opened up the online test. That will be due on the 9th of this week, or actually for you guys, it should be the 10th because my class meets on
Uh,
Tuesday. So the
okay,
practice
so
test
next
has been
Monday.
open. Yeah, the practice test has been open all week, and the other one that was open last week. Uh, Both of them were open last week, but the actual online test wasn't open until like Friday of last week. But you have multiple attempts, only your highest counts, and you got to get it in by the 10th at 11:59 p.m.
Oh, okay, that's just for the online.
Yep. And the next
Okay,
one, I'm moving all the other ones except possibly the last 2 weeks or the last 2 or 3 tests. I'm moving all of them back 1 week just to account for everything. I just haven't updated the
okay.
syllabus yet.
So the proctored exam isn't for a couple of weeks.
Yeah, you got a little bit of time. I wanted to get, I think I wanted to get 5 or 6 chapters in it before I actually did the first
Yeah,
one.
because we're going to cover the second law of thermodynamics next.
Yep. And that's a short, sweet one because our we've chosen as a department not to cover it at all. I just add it because I can't see not teaching a little bit about it at least.
Yeah. I mean, well, fortunately, I did. Chem 2 went over all of this,
Yeah,
so
that helps.
it definitely does.
Yeah,
Otherwise, it would
the more
be
times you see it, the lot easier it is.
agreed. Yeah, it's really hard to absorb the first time.
Yeah, exactly. All right, well, I'll go ahead and get back to this. If you got to split, don't worry about it. You're free to go. I'm going to keep talking to the air like I'm talking to somebody. It's like all my internal thoughts, but now
I
I'm allowed to do
I don't
it.
know how you do that, but
Yeah.
just pretend there's a crowd there.
Yep, that's it. Well,
All
in
right.
my head, there's always a crowd. They're like, "Yeah, do it." Yeah.
Okay.
That's just,
I don't.
hey, it's my head, man. All right.
Hey, no, yeah.
Well,
Anyway,
I will
all
see you
right.
next time, Josh.
Have a
Thanks,
good
bud.
evening.
All right. So we've now finished all that calorimetry stuff from chapter 18, and that brings us up to the first law of thermodynamics. And of course, I always remind my students, if you have in a course like a physics course or engineering course or a chemistry course, where there's like a whole chapter named such and such law, or just, if you have even, a whole subsection, or well, maybe not subsection, but a whole section of a chapter, if that's on something that has the big word law in it, you should be pretty sure that the very next test you do and all subsequent tests, you have that law, quote unquote, memorized verbatim. And then not only that, that you've thought enough about it to maybe even paraphrase it correctly. So, anyways, because of that, I'm bringing in not only the first law of thermodynamics, but I'm going to remind you guys what exactly the zeroth law of thermodynamics is, just so we can keep it consistent with that tutelage I've given you by suggesting that you definitely know the laws. This basically happened with me in grad school, in that the first test I had in grad school was in electrodynamics, and the instructor gave us a super nice, kind question, state, Maxwell's equations and the boundary conditions for them, and that was like a gift, right? But except I hadn't committed them to memory, and I hadn't done enough yet for them to just be stuck in my head, and I didn't do that well on that particular part. So I just, I hate to see an instructor work real hard to give students something nice and easy, and then the student miss it because they didn't know some of the quote unquote expectations. And one of the expectations is, like I said, you should always do your best to try to read the book. Uh, Two, you should definitely make sure you know all the terminology. Every time you see something in bold print, have that memorized. And then things with words like laws in them are things that whole chapters are devoted to, like Newton's first law of motion, or Newton's second law of motion, and Newton's third law of motion, or Kepler's laws of motion, or Newton's law of gravity. All of those things are such big, big names, and normally take up a whole chapter, or at least several sections in a chapter. So when they're like that, you definitely need to at least commit those specific laws to memory. So let's move on. The first law of thermodynamics is basically a conservation of energy statement. It basically says we have this concept of internal energy, which I've talked to you about before, but it's specifically all the energy that the atoms and molecules in any system, which, might be a cylinder of gas, and we're just focused on the gas itself. It might be the cylinder of gas and the gas. In that case, is a different system. And then the environment would interact with the outer system, stuff like that. But the main thing is a system is some area of the universe that we're studying. So if you're talking about an area of the universe that we're studying as a system, it turns out that it has a certain amount of internal energy in that system, and that is basically going at the microscopic level and looking at exactly how much energy in the realm of the various kinetic energies and the various degrees of freedom, the various degrees of freedom and of potential energy as well. So, for instance, you have for each of those bonds between two molecule or between two atoms in a molecule, that is a potential that looks a lot like 1/2 kx squared, and of course that fact that you've got an energy proportional to a variable squared is one of the ways that I use, or I teach my students to count degrees of freedom. So we've got that degree of freedom for kinetic energy as well. So you have a 1/2 mv squared term for that. But you also have all the other kinds of energy, like electric potential, that's associated with how far electrons are, if we can actually imagine them as infinitesimal balls orbiting infinitesimal balls that are slightly bigger, and that they have opposite charges, and therefore they have a potential energy associated with that. They also have a potential energy, though be it very, very small, due to gravity, because the gravitational force between the nucleus and the electrons is also a thing. So, in principle, all of those energies, all those, even nuclear energies, we know, for instance, the nucleus has energy states in some sense, in a quantum mechanical sense as well. So, there's energy associated with that. There's energy associated with the electrons moving. There's energy associated with the bonds. But if you add up all of those energies at that microscopic level, what you get ultimately is the internal energy. And that's what this is. The change in internal energy, that's delta E internal, is equal to the heat added to the system minus the work done by the system. I'm using very specific words there. The Q is heat added to the system. The W is work done by the system on the surroundings, in fact. So that's why I took time to write all this stuff out. And if you want to further see that it is a conservation of energy, we can combine the internal energy with mechanical energy, and we get this other version down here, which basically says that the total energy of the system, which is the kinetic energy, the potential energy, and the internal energy, the change in all of them is equal to the heat added minus the work done by the system. Now, again, I mentioned to you before that in chemistry, they use a different version. They have a Q plus W. And that's because they're using the work done on the system, because we were interested mostly when we were developing the science in the physical world. We were more interested in heat engines and stuff of that sort, whereas the chemists were more interested in energy to make reactions go or something along those lines. So it was more important for them to have a uh, estimate of the work done on the system as opposed to the work done by the system. So hopefully that's it. I did want to remind you, as I told you earlier, the zeroth law of thermodynamics. It basically says if object A is in thermodynamic equilibrium with object B and object C, that means A is in thermal equilibrium with both B and C. Then object B is in thermodynamic equilibrium with object C. So since B and C are both in equilibrium with A, B and C must be in equilibrium with each other. It's sort of like that reflexive property that you might have learned about in high school geometry that seemed like it didn't mean anything. It's like that in that we hadn't really thought of the complete logic of the situation until after we had developed a lot of science, so we had to go back and come up with a zeroth law of thermodynamics just to, you know, dot our I's and cross our T's. So that's basically it. We've run out of time. You can see I was getting ready to work example 4. Actually, I could do that real quick and then we'll call it a day. This one's easy enough. It says, what is the change in internal energy of a system if 2,700 joules of heat is added to it and 1,600 joules of work is done on the system? So this is where we're putting to good use that terminology that I told you about those words. So here's our solution. What we have here is delta E internal, and notice that's exactly what they're asking. What is the change in internal energy? So delta E internal is equal to Q minus W. We are told here that if 2,700 joules of heat is added to the system, so that tells us heat is being added to the system, so Q is positive 2,700 joules. And then it says, and 1,600 joules of work is done on the system. We're interested in work done by the system, so we're going to call that W negative 1,600 joules. So we can finally say that delta E internal is equal to 2,700 joules minus negative 1,600 joules. So basically that becomes addition, and we get 4,300 joules is the change in internal energy. So I hope that helps you. We've started off on a good foot with the first law of thermodynamics. We're going to next take various processes that we study in thermodynamics and in the physical world in general, and we're going to describe those, and then we're going to use those to reach conclusions about the new version of this first law of thermodynamics. In other words, we'll adjust it for adiabatic process, isochoric process, isovolumetric process, and so on and so forth. So I will see you guys next time. Don't forget, you do have a test due by 11:59 p.m. on, it should be Monday the 10th. If it's not, make sure you let me know. I'm pretty confident it is. So have a good one. Bye bye. Bye bye.